Hey everybody, welcome to lecture 26 of Electrical Engineering 331. In this lecture we will talk about a phenomenon that your book refers to as time-frequency duality. So we will start with example 26.1, and I'll say suppose that we want to find the Fourier transform of the rect of t over tau function. Now remember, rect of t is equal to 1 when t is between -1/2 and 1/2, and it's equal to 0 everywhere else. So rect of t over tau is equal to, well, you actually see it right here. Rect of t over tau is equal to 1 when t is between -tau/2 and tau/2, and it's equal to 0 everywhere else. And we would like to find the Fourier transform of that. Now actually the formula for the Fourier transform of this function is already in table 5-6, but this is a particularly important one, and so I want to work through it ourselves and then introduce some ideas to you that might be new. So if we start just with the basic definition of the Fourier transform of a function, it's equal to the integral from -infinity to infinity of that function times e to the minus j omega t dt. And so since this rect of t over tau is equal to 0 everywhere except between -tau/2 and tau/2, and there it's equal to 1, this integral can be written in this way. Now this is not a bad integral at all. This has almost the form of e to the u du, but we need a minus j omega on the inside and a 1 over minus j omega on the outside. And so then we can integrate this, and of course when you integrate e to the u du, you just get e to the u, and then we evaluate that from -tau/2 to tau/2, and so we will get this expression right here. And next, what I'm going to do is I'm going to take this negative sign here to interchange the order of these two terms in the bracket, in the parentheses, and so you can see that they've been flipped there. And the 1 over omega I'm going to keep out in front, but the j here, with 1 over j, I'm going to write that j in the denominator like this. Then I'm going to multiply on the outside by 2, and so and 2 in the numerator, and so then I have to put a 2 in the denominator, and I have this. Now if you look carefully, you will notice that this is just the sine of omega tau/2. This is that Euler formula for the sine of omega tau/2. And so we have 2 times the sine of omega tau/2 divided by omega. And now I will multiply the numerator by tau/2 and the denominator by tau/2. And so then we will have 2 times tau/2, and then this function, the sine of omega tau/2 divided by omega tau/2, that's the function that is probably new to you, is called the sinc function. And so in this case, that would be the sinc of omega tau/2. In general, what we have, sinc of t is sine t over t. Now this is called the unnormalized sinc function, and that's what we will use for this course. But you'll see in some courses they will use what's called the normalized sinc function, And that will be sine of pi t over pi t. Okay, but in this course, we will use this sec of t equals sine of t over t. And so if that's the way we define sec of t, then you can see that sine of omega tau over 2 divided by omega tau over 2 is just the sec of omega tau over 2. And so we then are finished. Remember, what we're finding here is the Fourier transform of the rect of t over tau. And so we bring that down, and we have found then that the Fourier transform of that is equal to, of course, we have 2 times tau over 2 is just tau. And then we have the sec of omega tau over 2. So that's an interesting result. And since you probably are not too familiar with this sec function, I thought let's investigate this a little more before we go to the next example. Now you think about this sec function, like I say, is equal to sine t over t. So what is that going to look like? Well, obviously at pi, and at 2 pi, and negative pi, and negative 2 pi, at all of those places it will be 0 because the sine of n pi is equal to 0. And likewise, another thing you can see is that the trend as t gets bigger and bigger is for sec of t to get smaller and smaller. So as we get farther and farther away, this function in general is going to be getting smaller. And of course, because of this sine t, it will be oscillating, as we can see. So basically what we have is these oscillations that are getting smaller and smaller in magnitude, and they cross the axis at multiples of pi. So all of that, I think, is pretty obvious. And by the way, one more thing that might be obvious to you is that this is going to be an even function of t. The graph certainly looks like an even graph, and the way that we get that is, remember, the numerator is an odd function of t, the denominator is an odd function of t, and so when you have an odd divided by an odd, you get an even function. The only question really is what happens, and so I've left a sort of a hole in the graph here, what happens as t goes to 0, because the sine of 0 is 0, and the denominator, of course, is t, that goes to 0 as t goes to 0. So as t goes to 0, this is approaching a form 0 over 0. Well, as we know, in a case like that, that's where we will use L'Hopital's rule. So let's see how this goes. So the limit as t goes to 0 of sec of t is the limit as t goes to 0 of sine t over t, because that's what sec of t means. And then we'll use L'Hopital's rule in going from here to here. And L'Hopital's rule says take the derivative in the top and the derivative in the bottom. So the derivative of sine t is cosine t, the derivative of t is 1, and now take the limit of this as t goes to 0, and we just have 1. So just as the graph sort of suggests, we just need to continue these curves on up here to 1, and we get that the sec function looks roughly like this. And once again, we see the oscillations crossing the axis at multiples of pi, and in general, the oscillations, as we go up and down, we're getting smaller and smaller oscillations because of that t in the denominator. So that's what sec t looks like. And sec t is an important function. It's an important function to know about. I mean, really, the fact that they gave this function a special name sort of gives you a clue that this is a pretty important function. Okay, well then, if sec of t is an important function, then you might say, well, maybe then it would be nice to find the Fourier transform of sec of t. And so that's what I ask in example 26.2 is, Well, can we find the Fourier transform of sinc of t? Well, if you use the Fourier transform formula, then you get that the Fourier transform of sinc of t is the integral negative infinity to infinity of sine t over t e to the minus j omega t dt. And as I say, this does not look like an integral that I want to evaluate. That doesn't look pleasant to me at all. So how might we evaluate this Fourier transform? Well, if you look up here at the Fourier transform pair, these two equations look a good bit like each other. I mean, there's this 1 over 2 pi out here in front of the inverse Fourier transform formula, but otherwise these two formulas look a good bit alike. And so we ask the question, can we somehow use the similarity of the formulas for the Fourier transform and the inverse Fourier transform to find the Fourier transform of sinc of t? Okay? So this is going to be a little bit complicated here, but just just bear with me. And once we have this done, we'll see how we can summarize this and make what I'm about to do a lot easier. But I want you to see it one time the sort of more complicated way. Okay, so anyway. So now, as we have already said, the Fourier transform of the reactive t over tau, we've derived this, is equal to tau sinc of omega tau over 2. That's what we derived in example 26.1. But since that is true, then our inverse Fourier transform formula tells us that the reactive t over tau, okay, well, it's inverse Fourier transform. That follows directly from this, but the inverse Fourier transform formula tells us that, the inverse Fourier transform of this is equal to 1 over 2 pi integral negative infinity to infinity of tau sinc of omega tau over 2 e to the j omega t d omega. Okay, that's the formula for the inverse Fourier transform. So we have this formula right here, and it may not be obvious to you at all why I would want to do that, but just just bear with me for right now. Like I say, all I'm doing is I'm using the inverse Fourier transform formula to write reactive t over tau in this way. Okay, now, in that integral, I have this omega tau over 2 right here, and I have omega appearing over here as well, and also in the exponent. So I want to define a new variable, and I'm going to call it, now, well, actually, let me say one more thing. Omega is just what people refer to as a dummy variable of integration. So we could call it omega, we could call it omega prime, we could call it lambda, we can call it anything we want to. And so what I'm going to do is I'm going to introduce a new variable of integration, lambda, which is equal to minus omega times tau over 2. Okay? And I'm assuming here, by the way, that tau is a positive number. Well, if lambda is minus omega tau over 2, then d lambda is minus tau over 2 d omega, which of course means that d omega is minus 2 over tau d lambda. So now, substituting into this equation, okay, we still have this reactive t over tau on the left-hand side, and we still have the 1 over 2 pi. And now notice, we have to be careful. In this integral, this negative infinity means that omega is negative infinity. But if omega is negative infinity, then since lambda is equal to negative omega times tau over 2, that means then that lambda will be positive infinity for the lower limit. And similarly, when omega is equal to positive infinity, then lambda will be negative infinity. Okay? Then we bring down the tau, and then omega tau over 2 is just negative lambda. So I have sinc of negative lambda here. And then e to the j omega t, well, since omega is equal to minus 2 lambda over tau, we can substitute that in there for omega. And then finally, d omega, we have found out, is minus 2 over tau d lambda. So I'll write that down for d omega. Okay. So now let's see what happens. Okay, to the next step, I'll just bring down this left-hand side. Okay, now what happened to the 1 over 2 pi? How has it become 1 over pi? Well, I have a 2 right here. So that 2 cancels with the 2 here, and that's how 1 over 2 pi became 1 over pi. Now, the next thing you notice is that the limits on the integral have flipped. How has that happened? Because instead of positive infinity on the bottom and negative infinity on the top, now we have negative infinity on the bottom and positive infinity on the top. How did that happen? Well, notice that this negative sign that I have right here is gone, and I've used that negative sign to flip the limits on the integral. Okay? Now, what about this tau? Where did it go? Well, here we have a tau in the denominator, so they canceled. Then the sinc of negative lambda comes down here, and the exponent here, I've just written things in a different order, but you can see that everything is still the same there. And I've already told you how everything in this was used, and then d lambda we bring down like that. Now, we're almost home now, almost done. Remember that sinc is an even function. We said that. So sinc of negative lambda, this sinc of negative lambda is the same thing as sinc of lambda. Okay? So I'm going to make that substitution in the integral, and I'm also going to do one other thing. I'm going to let t over tau equal beta. So when I do that, then this rect of t over tau becomes rect of beta, and I have 1 over pi here, integral negative infinity to infinity, and now it's sinc of positive lambda, because as I said, sinc of negative lambda is the same thing as sinc of positive lambda. And then the t over tau here in the exponent, we're going to replace that by beta, and so we will have this expression right here. And then we do one more thing. What we will do is we're going to let 2 beta equal omega, and we're going to let lambda equal t. And of course, if lambda is equal to t, then d lambda is dt. So when we make those 2 substitutions, okay, if 2 beta is omega, then beta is omega over 2. So we have rect of omega over 2 on the left-hand side. Here we have 1 over pi, and then we'll have integral negative infinity to infinity. And since we've let lambda equal t, this will become sinc of lambda will become sinc of t, and the lambda up here in the exponent becomes a t. The 2 beta, we've replaced that by omega, and then d lambda is dt. And so then that we have that, now we're just going to write this equation in reverse order and take pi over to the other side. So we have integral minus infinity to infinity of sinc of t e to the minus j omega t dt is pi times the rect function of omega over 2. But now look at the left-hand side. That is exactly the expression for the Fourier transform of the sinc of t. So we have found the Fourier transform of the sinc of t without doing a single integral, and it's equal to pi times the rect of omega over 2. Now, what we just did was is called using time frequency duality. You can look in figure 516 in your book, that term is used right there. Time frequency duality. And that's an important notion in Fourier analysis. Now, some people, if you look in some books about Fourier transforms, you'll see something called duality theorem. And I personally like the duality theorem. It makes what we just did a lot simpler, and it is applicable to many cases. So let's think about this duality theorem. Let's see how it goes. It's going to use time frequency duality, but it sort of summarizes everything much more compactly than what we did above. Okay, so recall that the Fourier transform of x of t, that's denoted as capital X of omega. Let me make sure it's very clear. Now, usually we have this little x is the function in the time domain, and capital X is the function in the frequency domain. So we have capital X of omega is the Fourier transform of little x of t, which means that it's equal to the integral negative infinity to infinity of little x of t e to the minus j omega t dt. And if we wanted to go the other way with this, then little x of t is the inverse Fourier transform of capital X of omega, and it can be calculated from capital X of omega in this way is equal to 1 over 2 pi integral negative infinity to infinity capital X of omega e to the positive j omega t d omega. So now what we're going to think about is taking the Fourier transform of that capital X. But capital X is now being regarded as a function of in the time domain, not in the frequency domain. Okay, so it's just like what we have up here above. See, in our first example, we had the rect function was in the time domain, and the sinc function was in the frequency domain. But then we wanted to know about what happens if we try to take the Fourier transform of the sinc function in the time domain, and what happens is we get a rect function in the frequency domain. That's the duality part. So let's see how this happens in general. Okay? So again, now we're taking the Fourier transform of capital X regarded now as a function of t. Well, we just used the usual Fourier transform formula. That's the integral minus infinity to infinity of capital X of t e to the minus j omega t dt. But then what I'm going to do is out front, I'm going to put a 2 pi, and then I'll have to put 1 over 2 pi. So, that's just like multiplying by 1, so that's not a problem. And so we have integral negative infinity to infinity, x of t. And now what I'm going to do is I'm going to write this as e to the jt and then negative omega. I haven't changed anything here. That's minus j omega t, and this is minus j omega t, but I've just written it in a slightly different form. Okay, and then bring down the dt. Now, look at that term in the brackets and compare it to the formula we had above. This is the standard formula for the inverse Fourier transform. It says little x of t is 1 over 2 pi integral negative infinity to infinity of capital X of omega e to the j omega t d omega. Compare this expression right here with what you have in the brackets. And you can see that the term here in brackets is going to be just little x of negative omega. See, here, the dummy variable of integration is t. Here, the dummy variable of integration is omega. So those two things, it doesn't matter what you call them. You could call them t and omega, or you could call them alpha and beta, or lambda and gamma, whatever you want to call them. But when you integrate this, you get this negative omega, where down here you have t. But otherwise, these expressions are exactly the same. So, like I say, down here you have t, up there you have negative omega. So down here where you have x of t, up here it's x of negative omega. And so once we have observed that the term in brackets is little x of negative omega, then we have our final result very quickly. F, the Fourier transform of capital X of t, is 2 pi times little x of negative omega. This formula right here can be used for any Fourier transform pair. Not just sinc and rect, but any Fourier transform pair. So it is a very useful thing to know about. Some books call this the duality theorem. And it's just very nice because it essentially doubles the size of your Fourier transform table. Every time you calculate one Fourier transform, you can immediately reverse it, use duality to get another one for free. So it's a really nice thing to know about. And so the last thing we'll do for this lecture is now we will once again calculate the Fourier transform of sinc of t, but this time, instead of going through all of those steps that we had in example 26.2, we will just try to use this formula directly. Okay? So let's see how that will go. In example 26.1, we actually derived that when x of t is equal to the rect of t over tau, its Fourier transform, capital X of omega, is equal to tau sinc of omega tau over 2. We derived that. And so now we're going to use the duality theorem, which is right here, to verify our result from example 26.2. Okay, so using this function as little x of t, and using this function as capital X of omega, we're going to now plug that in to this duality theorem. So we will get capital F on the left-hand side. Remember, we want capital F. I shouldn't say that because it's just Fourier transform. So on the left-hand side, we want Fourier transform of capital X of t. So here we have Fourier transform, and here you can see that we have capital X of t, because here is capital X of omega. So capital X of t will just be tau sinc of t tau over 2, which is what we have right there. And according to the duality theorem that we proved up here, that's equal to 2 pi times little x of negative omega. So coming back down here, little x of t is rect of t over tau, so little x of negative omega will be rect of negative omega over tau. And then we have that factor of 2 pi there. Okay. So how do we get our desired result? It's going to be very quick. We're just going to let tau equal 2. And so on the left-hand side, that becomes Fourier transform of 2 sinc, and when tau is equal to 2, that cancels, so we just have 2 sinc t. And then over on the right-hand side, we'll have 2 pi rect of minus omega over 2, since tau is 2. And then we multiply both sides of the equation by 1/2, so we have Fourier transform of sinc of t on the left-hand side, and pi times the rect of minus omega over 2 on the right. And remember that rect is an even function, and we are done just that quickly. So the Fourier transform of sinc of t is pi times the rectangle function of omega over 2, which is exactly what we found before right up here, but with much more work. So you can see that this duality theorem right here is definitely something that's nice to know about. And again, I'll repeat, as I've already said, in a sense, the duality theorem doubles the size of your Fourier transform table, because once you get one Fourier transform pair, then you can use duality to get a second one. So I hope that you found that interesting. Those are some important ideas. You learned about a new function, the sinc function, and you learned about the duality theorem. And so I hope that that was of interest to you, and I'm sure it will be of use to you in test 26. So good luck.